Welcome to a lesson on parametric equations of a line in R3. A line that is parallel to vector v with components ABC that passes through the point x1, y1, z1 is given as x equals x sub 1 plus at, y equals y sub 1 plus bt, and z equals z sub 1 plus ct. So the components of the directional vector a, b, c are the coefficients for t. And the point on the line, x sub 1, y sub 1, z sub 1, are the constants in each of the three equations. Vector v is called the directional vector for the line, and a, b, and c are sometimes called the directional numbers. Let's take a look at a line in space so we can get a better idea of what we're talking about. Here we have a graph of a line on the XYZ coordinate system. And if we rotate this system, you can get a better idea of that line passing through space. So when we talk about the parametric equations of a line in space, we're talking about a line that looks something like this. Now there's one more thing we need to talk about before we take a look at some examples. Sometimes when graphing a line in space, using parametric equations, you may be asked to determine the orientation of the line. And this refers to the direction the points on the line would be plotted as t increases. So here's the graph of the line defined by x equals 2t, y equals 1 plus t, and z equals negative 3 plus 2t. We can see that as t increases, all three of these coordinates will also increase because the coefficients of all of the t terms are positive. More specifically, as t increases, so does z. And you can think of z as the height of the line. So as t increases, this line is moving upward. So we know the orientation of this line would be from this direction to the left, or in this direction here. There's one more form of a linear equation we should mention for R3. The parameter t can be eliminated to obtain what's called the symmetric equation of a line in R3. So this form of a line in space is a symmetric equation of a line. To obtain this, what we can do is solve each equation for t and then set them all equal to each other. Let's go and take a look at an example. Here we want to determine the directional vector of the line and 2 points on the line. Remember, the directional vector for the line is determined by the coefficients of the t terms. So the directional vector would have components negative 4, positive 3, and positive 1. Now let's try to find 2 points on the line. We can find the first point, we'll call it point P, by the constants of each of these equations. So the x-coordinate would be positive 3. The y-coordinate would have to be 0, and the z-coordinate would be negative 5. But they ask for 2 points on the line, so to determine one more point on the line, we'll have to select a value for t and sub it into each of these equations. So for the second point, let's call it q. If we let t equal 0, we're going to come up with the same point that we just found. So let's go ahead and let t equal 1. So if t is equal to 1, we'd have 3 minus 4, that would be negative 1 for the x-coordinate, positive 3 for the y-coordinate, and then for z we'd have negative 5 plus 1, that would give us negative 4. Now remember, there's an infinite number of points on a line. These are just 2 points that are pretty convenient to find. Let's go and take a look at the graph of this line. Here it is in red, and again, if we rotate this coordinate system, we get a better idea of the line's orientation in space. Notice the line is below the xy plane until t is greater than positive 5. So the orientation of this line would be from left to right as t increases. Let's go and take a look at another example. Here we're given 2 points on a line. We want to determine the parametric equation of the line and then also determine the symmetric equation of the line. So looking at the parametric equations of a line, we can let either of these points represent x sub 1, y sub 1, and z sub 1. But remember, to find the values of a, b, and c, we have to find the directional vector of this line. And we can do that by finding the vector in component form that would pass through these 2 points. So we'll call our directional vector vector v, where the x component will be -2 minus 3, the y coordinate will be +3 minus 4, and the z component will be -5 minus 7. So our directional vector, which will give us a, b, and c, will be -5, -1, and -12. And again, we'll go ahead and use the first point, 3, 4, 7, to represent x sub 1, y sub 1, and z sub 1. But we could use any other point on the line if we wanted to. So the parametric equations of the line passing through these 2 points will be x equals 3 minus 5t, y will equal 4 minus 1t, or minus t, and z will equal 7 minus 12t. And the last part of this question asks us to find the symmetric equation of the line. Let's go ahead and do that on this screen. Now we could go ahead and just use the form of this equation here, but I do want to show the connection between this form and the parametric equations. So our parametric equations were x equals 3 minus 5t, y equals 4 minus t, and z equals 7 minus 12t. So what we can do is solve each of these equations for t and then set them equal to each other. To solve this equation for t, we would subtract 3 on both sides and then divide by -5. For this equation, we would subtract 4 and then divide by -1. And here we would subtract 7 and divide by -12. Now that we have all these equations equal to t, we can set the right sides equal to each other, which will give us the symmetric equation of this line. So we'd have x minus 3 divided by -5 equals y minus 4 divided by -1 equals z minus 7 divided by -12. And now we have the symmetric equation of this line. I hope you found this video helpful. Thank you for watching.